both types of consistency. We have a hard consistency, which is what we generate every day. Soft consistency is there's no guarantees, and that may work for some situations. And that eventual consistency is usually where a lot of the NoSQL data stores will live. I'm not going to go over this in too much detail. We'll be in the slide deck, but it basically gives you some ways of tuning or what it means. So hard consistency is basically when the number of the read core and the write core are the same as your number of copies. And then eventual consistency is when your number of writes is at least more than one, but less than the number of copies that you decide to keep. And 3 tends to be the magic number here as far as the number of copies. If you're only keeping 2 copies, your data is not as secure. If you're keeping 4 or more copies, you're not necessarily gaining anything, but depending on the system, you can gain certain read performance advantages. So eventual consistency. So it means all replicas of your data will be consistent at some time. That may be in a few milliseconds, that may be in a few seconds. It depends on how many copies of your data you have and how large the cluster is, a lot of different things like that. And something to factor in. So for a lot of applications, eventual consistency works really well. So for example, if you're doing stock trades, you want hard consistency, right? If you place that trade, you want it now, you want it confirmed. You don't want to find out later if it executed at a dollar higher than you thought to buy it at. You're not going to be well happy. On the other hand, your checking account is an eventual consistency system, right? You write that check, you give it to Walmart or Target, they're going to process it, it's going to get to your account, and it's going to be reconciled eventually, right? Could be a few days, whatever. So you have to kind of keep that into account. So there's various ways that these data stores work with consistency. So some of them will do what's called vector clocks, which is a way of determining what happened first. Did this read happen, or did this write happen, or did that write happen? Basically tagging it with a big number. Some will actually use a little timestamp. Vector clocks are a little bit different than that. Another one is called read repair. So if you have 3 copies of your data and you have a read form of 2, and the database or the data store reads 3 copies, but one of those copies doesn't agree, it will go ahead and consider that a good read, and then it will go back and update that copy that was out of date. So it will update, it will repair itself on your reads. Gossiping has to do with the cluster taking basically hashes of the information that they have and gossiping or sharing that with other nodes in the system to say, hey, this is what I understand the data to be. Is this what you understand it to be? And if they agree, great, you're good. If not, then they will decide what's the right information, and they'll update themselves behind the scenes. The other way of doing it is essentially saying, okay, application, I got 3 copies of data, here's your 3 copies. You tell me what's a good copy, and then I'll put it back for you. So it's kind of touching on the idea of letting the application go ahead and deal with it. So we're going to run through some comparisons. On the left-hand side is our SQL column, and on the right-hand side is the NoSQL column. It's more fair to call the comparison more relational versus non-relational, or RDBMS, Relational Database Management System, versus this new thing that's not relational model at all. So first of all, the SQL Land came out of kind of the big box or vertical scale system. So in other words, if your database is too slow or you're trying to put too many transactions against it, you get a bigger box. And you keep getting the biggest box that you possibly can until you can't get a bigger box anymore. And of course, all the Oracles and MySQLs and Postgres and everything actually aren't really quite scalable, but this is kind of where the mentality that they grew up in. On the opposite side is, well, instead of having these big expensive boxes that are self-redundant, because I don't want that box to go down, I'm just going to go down to Walmart and I'm going to pick up the cheapest bunch of things that I can. I'm going to wire all these things together, and then I'm going to build the tolerance into my software so that if I lose nodes, I don't care. If they blow up, I'm good. Matter of fact, the attitude is, not only do I want my system to be tolerant of failures, but I want it to run and work well even while things are going up, right? So if you've got a cluster of 1,000 nodes and each node has four hard drives, you got 4,000 hard drives that could potentially fail, plus 1,000 nodes, plus all the other hard drives associated with it. You're going to be replacing hardware almost every single day. And how does your software work over that? How does it deal with that kind of situation? So we have query by SQL, which is a language we know and love and love to hate, depending on what we're trying to do with it, if it's cooperating with us as well. And in NoSQL space, it tends to be, doesn't tend to be any SQL. Some of them have SQL-ish type of languages with them, but a lot of times you're going to be working with a custom API on this side, or some kind of SQL layer. And then, so when we're doing SQL, basically what we're doing is we're taking the information that's in our database, right? We're moving it to our application. We're going to do something useful with it. And then, a lot of cases, we're going to put some information back, some updates or something. The opposite of that is a stored procedure where you take your algorithm instead, and you're going to put that in your database, in your data store, and you're going to have it run locally where all the information is instead. It's really good for your process block stuff. On the NoSQL side, they have something called MapReduce, which is a way of taking a particular algorithm, dividing it up over however many nodes that you have, running it in parallel, and then taking the results and aggregating and reducing them into some particular answer. So on SQL, we're used to do all of our ACID transactions. A lot of times you get either very little to no ACID or transaction support. A lot of times you do have ACID, but it's only for a single unit of work, a single quote, a single data. You don't have this over multiple units of work, which is, it can be a really very big deal. It can be a deal breaker. It just depends on your data and your application and what you can do, right? And then on the NoSQL side, we tend to have these eventually consistent types of transactions, which is quite a bit different from work. On the SQL side, we have advanced indexing, we have forward key support, we have strong locks, all these kind of things that make our lives very easy and the database doesn't lock to make sure our data is consistent and good, and all that fun stuff as well. So on the NoSQL side, a lot of times you don't have indexing, it just depends. Some have very strong indexing, some of them indexing doesn't really even apply depending on what the data store is. Same with indexing support. If you've got a document store with key values, you've got a key value, some of the stuff doesn't really quite apply. Schema, we love all of our RDBMS schemas, especially when we have to run all our update scripts. We have to test them against all the development servers. We have to test them against our QA servers. We have to test them against our staging servers. And then we got to roll all this stuff into production. It's a big pain. It's a big headache. A lot of these systems support either schema doesn't really apply, or they implement a very flexible schema where, if you want more columns, great, go ahead and add the columns. To the point of even referencing a new column, and be able to add that new column for you. But it's very easy to do, and it kind of avoids some of this pain that we have. So as far as APIs, we have JPA, we have JVC, we have Hibernate, we have all these fun things that we deal with. A lot of times on the other side, now it's depending, a lot of times you're going to have a custom API. A lot of times you'll have the best API that you can work with. But there's convergence. We're trying to move towards the stuff that we know now to make it easier for us to work with, a lot less expensive to be able to implement. And then also on the access control, RDBMSs have a lot of access control. Most NoSQL data stores have absolutely zero access control. So you have to be careful. You can have anybody come in and start looking at all your data, so you don't want to expose it to the web or anything. You've got a REST interface, and you can have anybody issue with root command go against your data. Obviously, that's a very bad thing. So the last slide I have on this, SQL systems tend to have a very complex on-disk representation of access. So for example, on Oracle actually would love it if you just gave it a bunch of disks that are raw then we handle everything for